In this video, we are going to be going through the introduction for lesson 20 on area and definite integrals, and we will be doing the warm-up. The warm-up is remembering some stuff from lesson 19. All right, so in the previous lesson, lesson 19, we studied antiderivatives. We were asking ourselves the derivative of what function is the function that they are showing us here. And another name for those antiderivatives is our indefinite integral. Get some highlighter. In today's lesson, we're going to deviate from this discussion a little bit. We're going to be talking about how to approximate signed areas under curves. And by a signed area, we mean an area that could be either positive or negative. And we'll talk about why we might want to have negative area. And we're going to formalize our discussion of this approximation using Riemann sums. We're then going to discuss how to make our approximations exact with a special kind of limit. And that limit is going to be called the definite integral. All right, so we're going to be learning about Riemann sums to approximate areas, and the definite integral to get the exact area. That exact area. And we won't be evaluating those limits, but this is setting the stage for our next lesson, one of my favorites, the fundamental theorem of calculus, that'll tell us how to evaluate the limits like this. Okay? And it's exciting, I promise. So today we're going to learn about Riemann sums. We're going to estimate areas under curves. We'll get our limit definition for the definite integral. And then we're going to understand some properties of definite integrals and use geometry to evaluate definite integrals. They are areas under curves. And we're just going to be getting practice mostly looking at that integral notation and reading an area. Okay, so let's jump into the warm-up, remembering the stuff that we did in our last lesson. Find the general antiderivative, right, of this function. So I'm asking myself, the derivative of what function is f? Before I go ahead and jump into that, I see that f is composed of one object, one function of x, minus another function of x, plus a third function of x. That's great. I can compartmentalize my thinking because I have terms here. Before I get to that, though, to think about the derivative of what function is 1 over x squared, it will help me if I write 1 over x squared as x to the minus 2 power. Now my antiderivative going term by term, the derivative of what function is negative sine? The derivative of cosine is negative sine. Minus the derivative of what function is cosine? Well, the derivative of sine is cosine. And then plus, here we're going to do power rule in reverse. How does that work? I am adding 1 to the exponent and dividing by that new exponent. So I'm adding 1 to negative 2. And then I'm dividing by that new exponent. I'm going to I know we can do this arithmetic in our head, but I'm going to write it like that in our notes so we can kind of remember this is a brand new rule for us. What is our thinking here? All right, before I clean it up, what did I forget intentionally? I forgot a plus c. The general antiderivatives all have those plus c's. Why? When I take the derivative of this, going term by term, Derivative of cosine is minus sine, check. Derivative of minus sine is cosine, check. We're going to clean this up. And the derivative of plus a constant is 0. And adding 0 doesn't change anything. So all your general antiderivatives will always have those plus c's. Let's go ahead and clean it up. Minus 2 plus 1 is minus 1, so we have x to the minus 1 power all over minus 1 plus c. And finally, just making it look nicer, minus 1 over x plus c. All right, so there is that general antiderivative. I want, instead of us always having to prompt the reader to find the general antiderivative, we have another notation for asking that question, and that's the indefinite integral. And I was using green for my F last time. Right, so how could I ask myself, or ask you as a student, the derivative of what function is green? I can ask that with this indefinite integral notation. These two symbols partnered together are saying the derivative of what function, or more specifically, what family of functions, is the green function right there. Right? So being asked to find the general antiderivative of f of x is the same question as being asked to find this integral, this indefinite integral of my green function. Geometrically, our solutions here are the whole family of curves whose derivative is the green function. So this represents the family of curves or functions here. What's so special about them? Their derivative is that f of x. And I'm just going to write f of x right here instead of writing out the whole minus sine x. Okay, let's look at that link real quick, and then I'll conclude this video. All right, so here in red, we have a antiderivative, right? That's the function we came up with, cosine x minus sine x plus a minus 1 over x, or just minus 1 over x. And then the general one has the plus c. Notice that shifting that red curve up or down, that's what the blue curve is, it's just that vertical shift, does not change the derivative at a particular x value in the domain. That's what the green dot is showing you right there. Here I'm at x being minus 4.8. The slope of the tangent line to both of those curves is the exact same slope. And that's true for all x values in the domain. All these lines are parallel. The derivatives at those points on both functions are the exact same number. Okay, so hopefully this kind of refreshed your memory from lesson 19 and set some of the stage for the things that we're going to get accomplished in this lesson. Thank you for watching.